Yes, sir.
So instead of indices being discrete, here the indices are continuous. That's it. Okay, let's see if our momentum operator. Okay, let's see if position operator is Hermitian. Well, the position operator x hat xx prime is x delta xx prime. Nobody stopped me because there should be a star here. No, sorry. No, there shouldn't be. Yeah. Yeah. So, so if I take the Hermitian conjugation of this, x dagger, its xx prime element is going to be x star x prime x. But what is x star? This is real, right? So it's just going to be x. And this delta will be x minus x prime minus x. But we already know that this is an even function. So I can write this as delta x minus x prime, which is simply the operator x, xx prime. So yes, we have proved that the position operator is a Hermitian operator. Okay, very trivial. Less trivial is the momentum operator. So the momentum operator, we saw its xx prime is given by h bar by I d by dx of delta x minus x prime. So if I take its conjugate, Hermitian conjugate, and ask what its xx prime is, well, it should be p hat x prime x complex conjugation. But what is this thing? This thing is h bar by I d by dx prime delta of x minus x prime Hermitian conjugation. Sorry, a complex conjugation. So if I take away the bracket, I get a minus h bar by I d by dx prime delta of x prime. But we can use that identity to make the derivative with respect to x, and then I get a plus minus sign, extra minus sign, so I get an over a plus sign, so I get h bar by I d by dx delta of x minus x prime, which is p hat x prime. So we see that the momentum operator is also a Hermitian operator, okay? But unfortunately, this is not enough. Unfortunately, well, not unfortunately, that's just the life is. For operators, are defined. Okay, let me just rephrase that. For operators to be well defined, they also, or we also, need to specify the domain on which they act. And so far, we haven't said anything about the functions that they can act on. So in general, Hermicity means that if I take an operator, act it on some function, and take its inner product with another function, then that is going to be equal to its Hermitian conjugate acting on the same function, right? So it turns out that this is more restrictive than this. Let's see how this is so. So let's do it for P. Is that psi P dagger of phi is equal to P of psi of phi. Now, if I take the right-hand side, P of psi of phi, and take its complex conjugation, then what do I get? I get phi of P of psi, right? And if I say, and what is the, what is the transpose of this thing? The transpose of this thing is exactly this thing, right? So in that sense, the definition of Hermitian conjugation of an operator is this thing. Okay? Does that make sense?
Yes, sir.
So if I now write the right-hand side, so the right-hand side is d of x. This thing is just phi. What is this thing? This is h by I. The derivative with respect to x of psi, and the whole thing has to be taken the complex conjugate, right? So then d of x, so yeah, I just figured it out. That's why I'm carrying on. So this is h by I. The I becomes minus I once you enact the conjugation. And here you get d of dx of psi star. And then what you can do is that you can do an integration by parts. If you do integration by parts, then you get d by d of x. There's a minus sign, and there's a h bar by I. And inside there's a psi star of phi. And then you get plus of h bar by I, d of x, psi star, d of dx of phi. But the second term here, the first term is a total derivative. So if I integrate this, this will go to 0 if psi and phi go to 0 as x goes to infinity, right? Does that make sense? The first term will go to 0 if psi or phi go to 0 at infinity, because it's a total derivative. So the integral will, we have these limits here. So the first term is 0. What about the second term? The second term is psi p of phi, right? So if I compare this with this thing, we see that we have proved that psi p dagger of phi is equal to psi p of phi. That this is Hermitian, but for this to be true, we needed to impose this condition, right? So for this to be true, we need to restrict our attention, or the operation restrict the action of P to wave functions that go to 0 as x goes to infinity. And such operators are called self-adjoint. Okay? So for infinite dimensions, we not only need the operators to satisfy this condition, this condition, we also need them to act on wave functions which go to 0 as x goes to infinity. And remember that we want psi and phi to be L2 integrable. So that is satisfied, right? So this is satisfied. So because for L2 integrable functions, we do want those wave functions to go to 0 as x goes to infinity, and therefore they are, Hermitian. So it is self-adjoint. Okay. Okay. So tomorrow, your midterm will be from 10 a.m. to 10 a.m. of the day after. Okay. If there are any issues, you can always message me. Okay. Any other questions or comments?
No, sir.
Well, it's late, so let's end the class here. Okay.
Okay, sir. Thank you.
Okay.
Bye.